So one of the things we always see is people really having great demos, and I'm pretty sure you've seen it all over the internet as well. Demos of robots doing crazy things, AI doing amazing visuals, just demos coming out of from companies, and then in real life, they're never used, they never work, and sometimes they're even shelved. I talked to someone a few weeks ago, and he told me that 90% of those demos being created, which work in a closed environment, they never see the real life. Why? Because there's several problems with this. Once, they don't work in real life, and the other thing is they don't even have a good application. And that's why we have this topic here today with Clemens from RobCo, where we talk about lab demos versus real work and real factories. So because that is something which I've seen, something that's really special about RobCo is that you're creating these robots, these autonomous machines in your in the office where you're all staying right now. And basically the interesting part is it's also integrated and very near to real life application. And what I think is what I'm interested in, what is the real challenge when robots move from controlled labs into these massive factories? Because I always think factories are these clean spaces where everything is controlled and works, but in reality it's not, right?
No, in the end, the proof is in the pudding, or it's always a hypothesis how you build things. Once you move there, the environment changes, the challenges are bigger than you had before, and then you need to make it work.
Yeah, absolutely. So welcome to the RobCo podcast, because that's where we talk about, physical AI and autonomous robots. And I just want to say hello to you, Clemens, again, from RobCo. And he is one of the principal engineers, but he's definitely leading the whole space where the robots are being created and programmed that they can work, for you and create the future of physical AI. Let's move on to the questions. Why are impressive robot demos often misleading when it comes to real industrial deployment? And that's also something I led in with the intro, because I love this topic. Tell us a bit more about that.
Well, if you have a demo, especially on video, then obviously it can be cherry picked.
Yes.
And oftentimes when you're dealing, especially with data-driven demos, it's relatively easy to get to success rates of 80 to 90%. And then it takes another time, the same development to get to 99%, and so on. And so recently, a very famous researcher in the field said, it's basically adding a 9 always adds as much of development effort. So what we're trying to do is make this process easy and fast, and but we need to be able to show that ourselves when we do, the development ourselves.
Yeah, I think that is something really important. When you're optimizing for 99.99999%, every 9 that you add takes a lot of effort, right? And that's why autonomous driving isn't solved yet fully, because it's at 99%, at 99.999, I don't know how many nines already, but not fully. That's why, some of the accidents still happen. And I think that is something that's also really important. You when you're solving for these in a demo environment, it's very easy because it's very, very controlled, right? And there's nobody running through, there's no changes happening, there's no age happening as well. And in the real life, it's very, very different. And so you obviously deploy in factories, and then you get the feedback loops as well. But what makes it so much harder in these factory environments? What are the biggest challenges happening in the factories?
It's easier and harder. So I think autonomous driving is a case where you say, is this AI complete? Do you have to solve all of AI in order to deploy anything? So I think what we've seen is that it's actually doable, right? If you just work really hard and for many years. For us, we have tried to simplify the problem by restricting the type of problem that we want to solve. So, for example, if you deploy in a particular setting in a factory, you have to solve a much easier problem than if you deploy it out in the streets, or in a in a kitchen where things are messy.
Yeah, we're changing environments. Huh?
Exactly. So we can still control the type of problem that we wanna solve. It's not that there are no problems out there. Like, we're getting bombarded with customer requests. Build us the AI robot, but can you solve this? There's things that we cannot automate with traditional robotics. Um, and so, uh, but in the end, it's all about atoms. It's all about the real world, and then you find these situations where something can go wrong. Either it's on the hardware side or it's on the software side. Simple things like dealing with very diverse set of objects, and suddenly the gripper solution that you had built doesn't work anymore, and
Hmm.
so suddenly you need to adapt that. And there we're talking about sometimes cases where 99.99% is not even possible, right?
Yeah, of course. Why is reliability often more valuable for factories than impressive robotic capabilities?
I think it's the expectation from somebody who wants to automate a solution is often that it works 100% of the time, and then the value diminishes very quickly when it's below that,
Hmm.
because now you have to have a person on staff who can deal with all the issues. You might have production lines that cannot stop easily, and so suddenly the whole question, couldn't you have a human there, because humans are adaptable
Absolutely.
and can solve these problems on the spot, might actually then make more sense.
Yeah, it's really interesting because the it's not about doing it once, but doing it many times, and the imperfections. Obviously, we want to minimize them, but you really need the reliability across thousands and thousands of repetitions of the same task, right? And yeah, so the the thing that I always find interesting is how many real world developments does it really take, real world deployments in the factory does it really take for the system to become truly robust? Is it like is it like the first time does it already work, or does it take like many iterations until it becomes really robust?
It depends on how much experience you have in a certain case,
Hmm.
and obviously also the how challenging the task is. We have certain tasks like palletizing, for example,
Hmm.
where we have a very robust system that can deal with all sorts of challenges. If you do things for the first time, it might take additional development effort and a very strong tracking of metrics in order to make it work.
Yeah, for the tracking of metrics, that's I think something that is very interesting, and maybe that's also the reason why you did it. So RobCo is implement systems end to end, so from production to deployment, whereas many other robotic companies they just sell robots to resellers and to integrators. Is that one of the reasons why you do the end to end integration?
Yes. So for me, a company like RobCo is an information processing system.
Yeah.
So for us, the best way to get the feedback loop going is to is to make the feedback really short. And by short, I mean literally, because right now people who are deploying are sitting on the same floor as the people who are developing the
Hmm.
robots. And so we have this loop in place where we learn all the time and every day.
Yeah, that's really interesting. And so the acceleration that you get from the system improvements, it must be really high because you have the connection of the people sitting together, but also you get the data from the real world, right? How can you integrate that data, or can you use that data?
Yeah, I mean, obviously it depends on the customer
Hmm.
case, but I think there's a lot to be said about how much extra value we can get by being able to process the data to make the system overall more robust. And so for that, we have the possibility to record the data, also to select the cases where something interesting happens,
Hmm.
and then be able to use that for further improvements.
Very interesting. I've seen the testing lab in RobCo.
Mhm.
I've seen the arms move and everything. So that's the pre-production setup, right? That you use before you deploy, right?
Yes, it's after production, but
Yep.
it's we run every robot for 48 hours
Hmm.
to make sure there's no initial breakage of any component.
And do you already have data coming back from that machine that you can feed back into the system, or is it?
Yes, we can. We are storing all the telemetry logs from that, and so we can react accordingly.
Very interesting. So when we're looking at especially like the data generated in the field and that you can use, we just talked about, that definitely helps a lot because then you're getting, I mean, I think it's like the one of the most important things for autonomous cars as well is like generating all this data, the camera data or the infrared data to understand certain situations better. Is this the same with the robots at RobCo, that you have like this obviously the same thing over and over, the data stays relatively the same, but is it like the exceptions that are interesting that you're working with and that you can generate, improve the models that you're working with?
Mhm. So it depends. So what we're currently doing is working on these level 3 and level 4 autonomy cases. We talked about it last time, where it is absolutely vital, or it's a core part of the whole system, that we get all the sensor data that we get, because suddenly you're not just a robot that executes something.
Yep.
You're a robot that is processing all of the information from the sensors all the time, many times per second. And so obviously it is important that we keep the data as it is necessary for improving a certain task. This might also include the operator being able to step in
Mm-hmm.
and correct for errors. And these are the most interesting cases, because then immediately we get some feedback if something goes wrong. But it might also be that we can connect it to an external sensor that gives us a feedback signal whether something was successful or not.
Interesting.
Right. And so this way we can, funnel that back into the feedback loop.
Oh, that is very interesting. So you can basically take all the data that you've seen that was wrong or off by a certain measurement, and then feedback and correct and play it back to the user, to the customer. And then it's probably just a software update, right? So the customer doesn't have to redeploy anything, usually, I guess, but just gets a update and is ready to go again.
Yeah, I mean, for us, it's important that the customer is in control, right? But we can then, update. Usually, it's a model update.
Yep.
And so this way we can put in, new versions of the model. If it is corrected right away on the robot, it's even simpler. Then directly while the correction is done, learning takes place on the robot, and so basically what we're just updating is weights in a neural net.
Yeah. Maybe explain to me a little bit more how the system works with closed learning loops. How can I understand this? So physical AI improves obviously through closed learning loops, and how does that work? How can I understand this better?
Yeah. So when you correct a robot, then the first bit of information is something goes wrong. And so then the robot can compare how it would otherwise have moved
Interesting.
with how you made it move.
Yeah.
And so from this delta, that's what learning is all about, finding out deltas between what you would have done and what you do.
Yeah.
And so now the delta is, you can, what we call back propagation. So we can propagate all the errors back through the whole neural net. And at every step, there's a slight weight update. And in the end, at the end of the update, the neural net will behave differently than before.
Interesting. I never thought of that process being that, but it's basically like having a human trainer who's telling you, okay, you have to do it like this, and then you know your deviation, or at least the trainer sees the deviation. But obviously, as a machine, you can see it yourself, even though you're deviating from the course. It's very interesting.
It is all modeled after human learning,
Mhm.
although, of course, the implementation is very different. But we're trying to find out, we as in the community of people who deal with learning problems, how to do it as efficiently as the human does it.
So when we're talking about humans, we have this topic of the digital twin, and how does that work with robots at RobCo?
Yeah, so here we need to distinguish between the different levels of autonomy that we
Yeah.
defined. At its core, RobCo makes modular robots, and so even if you just assemble a robot, the robot controller already gets the information how it is comprised
Mm-hmm.
and certain aspects of the physics that it needs to operate the robot in the first place. Because if you don't do that, then and you turn off the brakes, the robot would just fall down.
Okay.
Right? So the simplest thing that it needs to be able to do is to know its weight and to counter the forces just from gravity.
Okay.
And this applies to all of the robot control problems. And then when you talk about, for example, path planning or computer vision integration, then you add certain elements of the physical world into this digital twin so that you can deal with it and react to it. This is often done in certain optimization problems. So you want to find the shortest path from A to B, given that there's some kind of obstacle.
Mm-hmm.
So this is the I would say the digital twin that we need when we want to deal with these first layers of autonomy that are in production, that are usable by clients, and that are also still improved. Like we have active teams that are working on improving them, making that more simple. Now, when it comes to physical AI, which is the next step of development that will be the dominant piece in the next few years, then we're talking a much more subtle representation of the world that is in some sense baked into the neural nets themselves.
Okay.
So in order to execute a certain task, the model needs to understand physical aspects of the world, how geometry works, how physics works, and how materials work when I want to interact with them. So the digital twin is not expressed in code and vectors and points anymore. It's inside of the neural net as an emergent property because we have trained it on a lot of data.
So interesting. So is it basically like, do I have to understand the digital twin being just a virtual representation of the robot doing the same things, and then basically them combined? So the software, the digital twin is the brain, and the robot is the body of that brain. Is that a correct representation in the in level 1 and level 2? And then in level 3, or getting more to physical AI, basically, is them more like you don't really need this digital representation, like where it's has an exact path and exact movements and everything, but more than it evolves into being an open model that can understand its environment fully.
So I would phrase it this way: the digital twin is a little bit like what a map is to the real world.
Okay,
that's
a good example.
So what do you put in a map? You put in the map the information that is relevant.
Yes.
For example, if you have a road map, you don't care about maybe the restaurants along the way, right? If you're talking about a traditional roadmap, but you care about the distances. I don't know. Nobody uses road maps anymore. Everybody uses these.
It's a great example, to be honest. Yeah, because if you have you could have a roadmap that is specifically for restaurants, and you could have one obviously that's specifically for distances.
Yeah, exactly. And so the term digital twin comes from the aerospace, where you need to understand the physics of a wing of of a plane, or how the engine works. So this is like 40, 50 years ago where these first simulations came about. And obviously then the digital twin is only as good as it represents the environment accurately.
Okay.
Right. And so we have all the tools for doing that. For robotics, it's probably a little bit simpler. We have the physics of the robot. We have certain objects which we want to represent, but it's important to be able to have them for executing a certain task. Now, for physical AI, as I said, all of this is not given up front. It needs to be understood by handing it a lot of data. And the interesting thing that we see from large language models is then that in order to solve the problems that we wanted to solve, it needs to build a digital twin inside. Otherwise, it wouldn't be able to solve the task.
Interesting. Very interesting. So let me ask one more question about this topic, because I find it really fascinating to understand it. So we as humans, we can walk into a crowded place like an airport, and we can focus only on the relevant information. So we have shops there, we have escalators, we have people running around in different areas, all having their own agenda, and we can focus on the timetable and the gate we have to go to. So we're very good at canceling out the noise or canceling out not important information. How do you do that in physical AI in the digital twin? How do you do that? Because when you're getting all that sensory data in, I believe it's definitely a task to filter all that, because you need to be focusing on what's relevant and how do you identify that. And the processing power must be crazy as well.
Yeah, it's a very good example. I'm totally on autopilot in airports, and I never know which airport I'm on, but I still can find things around. So I mean, this is where the big leap that the learning community has dealt with is being able to build models that do exactly this kind of filtering while learning things. I mean, this is the core of the so-called transformer architecture.
Yeah.
That there's a part of the network that only deals with selecting from an equal list of things to select from, which might be tokens in a long text.
Yeah.
But it might also be the internal representation of some abstract concept that it has come up along the way. And it learns how to put these filtering, these little filter masks around the pieces that are relevant for the particular thing. And if it does it wrong, then every time it does it wrong, it gets a feedback, hey, you did it wrong. And then it figures out, how to correct things in the best possible way in order to make it better next time.
And this correcting is, again, the closed loop, right?
It is the closed loop. Yeah, it's all about getting towards an end state, and then we need to have a means to find out how far away is it from the desired state. And then you have this kind of delta, and the delta flows back through the whole thing, and you can do that multiple times per second, and this way it learns.
Clemens, thank you so much again for explaining this to me, because that's something I read about so much. I heard so much about the digital twin, but it's really sometimes hard to understand what it actually means. So thank you for diving deep into this topic again with me, and diving into already what the difference is between, lab results and real life results. I think that's really important. And I think RobCo is one of the manufacturers out there, and I would say more like full end-to-end solution providers that, can actually really do everything and deploy not just a lab result, but a real manufacturing result. And obviously, if you're listening right now, we'd love you to subscribe to our podcast, also to our newsletter, and join us again when it's the next time RobCo podcast. But I have one last question for you. It's a bit more open world question, big picture question, because I think that's a good way to close this podcast off. Is what will people misunderstand about physical AI over the next 5 years?
So I think there is a common misconception that if you see a humanoid, that it is like a human.
Yeah.
And obviously the humanoid needs to use physical AI to do anything because you can't program it.
Yeah.
But a human has evolved for millions of years. It has skin that has self-repair. It has all these sensors in every finger. And the misconception is that just by having a humanoid do something, that it can replace humans. We see these demos in where there are humanoids doing kung fu dances.
Yeah,
but these are more like puppets, right? They're not even zombies. They have really no brain at all. So I would say we will hopefully learn to make that differentiation. And then really be able to make use of the benefits of physical AI and expand the things that we can do, without having scores of cheap workers somewhere that are working in terrible conditions. But we can do interesting and much better products this way.
Thank you so much. I love that so much, because I think most people think we're really close in having humanoids doing everything for us, but I think we're quite far away, because we talked about some other time how difficult it is to have touch working in a humanoid robot, and also having it understand its world and really interacting in a proper way is much harder than it seems. And obviously all the videos you see on YouTube, they're amazing, which shows like this robot can do this, but in reality, it can do it once or twice. And in a factory setting, it's required to do this hundreds of thousands of times in a reliability. And this is not given with these demos that we see.
Mm-hmm.
Thank you so much, Clemens. And anything else you want to add?
No, thank you for having me.
Yeah, thank you again. It was so much fun. And we hope to see you all again when it's again the RobCo podcast, where we talk about physical AI and the advancements in robotics. Thank you so much for listening. Thank you, Clemens.
Thank you.
And see you next time.